Hello, everyone. Welcome to the next theory lunch talk of our semester. Today we have CJ, and he's going to tell us about this exciting new result on chasing convex bodies. So welcome, CJ, and thank you for coming.
All right, thanks for the introduction. I'm just very excited to give this talk. This is a very fond work of mine. Sorry, am I off the screen? How far do I have to move? Right here. Okay. Sorry about that. Okay. Let's start again. All right. So thank you all for coming. As I said, very excited to talk about this work. So here's the problem. I'm working in d-dimensional Euclidean space. I start at the origin, and I'm given some convex set. And once I see that, I have to pick some point in that set, and I move there, and I'll be charged the distance that I moved to get to that new point. Once I've done that, I get a new set. Pick a new point, move there, again I'm charged the distance, and I just keep doing this until I stop getting convex sets at some point. And the goal here is to compare myself to the offline optimal, which now gets to look at all of the sets up front and then find the best possible path to visit all of them. And we'll have some length which is shorter than mine, and the goal is to get my cost to be as close as possible to ops cost. So that's the general problem. There's an important special case of this called the nested problem, where it's the same problem, but each time the convex set is a subset of the previous set. So you keep on narrowing in on a smaller and smaller area. And one of the things that's nice about this is that it's very easy to optimize in the offline setting. Since the optimal algorithm has to get to the last set eventually, it may as well go there at the first time step and be feasible for the rest of the time and just sit there. So the optimal algorithm is just whatever the closest point is in the last set. And this has proven to be an instructive special case in understanding the more general case of the algorithm. So we'll talk about this a lot throughout the talk. A formal definition of the problem: an instance consists of a sequence of convex sets. I have to choose my point xi in ki in an online fashion, meaning that I choose xi before ki plus 1 is revealed to me. The cost of the algorithm is the sum over all time of the distance of xi from its previous point. And the goal here is to minimize what's called the competitive ratio, which is the standard metric of measuring how the success of an online algorithm, which is I take the ratio of my cost on an instance to ops cost on that same instance and maximize that over all possible instance to get the competitive ratio of the algorithm. I want an algorithm whose competitive ratio is as small as possible. It's never going to be less than 1, so as close to 1 as possible. Yes?
How are the convex sets given to you? By an oracle or?
Let's not worry about that quite. Let's just say they're given to you however the most powerful way you want them to be given to you is. So for computational issues, we're not really going to dive into it. It's more information theoretic type of result. So a couple motivating other problems. So the first one is called function chasing, or it's also called in the world of machine learning, it's called smooth online convex optimization, or SOCO. And this has been pretty widely studied. And it's a very similar problem, except instead of getting convex sets, you get convex functions. And so now that you're not restricted to a feasible set, you can play any point you want in RD, but you incur the cost of the function at the point that you move to. So you're given the function, you see, I want to move to some point where maybe the function cost isn't that big, but I'll be charged both for my movement and for the cost of the function at that point. And it's easy to see that this generalizes convex body chasing because the function could be 0 on a convex set and infinity everywhere else, and then I have to play a point in that set and the fi term and the cost goes away. But they're actually equivalent problems up to maybe some constant factor, and this reduction was shown in a paper that we will reference many, many, many times throughout this talk, so get used to the names Sebastian Bubeck, Yin-Tat Li, Yuanji Li, and Mark Selke. A next motivation is the metrical task systems problem, which is similar to function chasing, except instead of working in RD, I'm working in a finite metric space. And now, again, instead of playing an arbitrary point in the reals, I'm playing an arbitrary point in the metric space, but the cost is the same. It's the movement cost plus the hit cost of the function. And this is a fundamental problem in the world of online algorithms that's been studied a lot over the last 25 years. And the convex body chasing problem was originally introduced in order to study MTS, to kind of isolate the role of the geometry of the metric space, ignoring the shape of the functions. So historically, that's where the body problem came from. And then the third motivating problem is the paging problem, which is another kind of classical problem in the online world, where you're given, there's a total of n pages that you have to keep track of, and you have a cache that can hold at most k of them, or k is some number less than n. At each time, you'll be requested a page that you have to have into the cache. So if the cache is already full, then you have to kick something else out of the cache, and you have to decide what to kick out and move that page into the cache. And the fractional version of paging can be seen as an instance of convex body chasing, where you can think of my feasible set is all points with mass k, where the mass kind of represents my allocation of the spaces in my cache to various pages. And at time t, when I request a page, I have to allocate an entire spot of the cache to that one point. And this, the paging problem generalizes to the k-server problem, which can be thought of as doing paging where you're, rather than working on sort of uniformly distant pages, you have an arbitrary metric space. And this itself is also a fundamental problem in the online algorithms world. And I would add the last bit of motivation for this problem is it's just, in my opinion, a very clean, nice problem, and one that I had a lot of fun working on. So I think it's just a good problem by itself. And before I get to the results, I want to give the classical lower bound for this problem, which was given by Friedman and Lineal, who were the first ones to study convex body chasing. And it works in an arbitrary dimension d. I'll illustrate it in 2 dimensions. You start in a hypercube, and you're given progressively faces of lower dimensions. So here the first convex set I'm given is just one side of the square. And really the only sensible thing to do is to project onto that side. If I try to go to one side or the other, then in the future I'll just be given things that are opposite the side that I chose, and I'll end up having paid more for having tried to cheat to one side. So I just project, and then in the next step I'll get a face of 1 dimension lower, which in this case is a point. And for 2 dimensions, the algorithm played the 2 sides of an isosceles right triangle. The optimum played the hypotenuse, so the algorithm is paying square root 2 times the optimal. And in general, you end up paying square root d times the optimal. And this gives a lower bound of square root d on the competitive ratio of any algorithm. So square root d is the target, and this lower bound has really not been improved ever since then. So square root d kind of remains the target for this problem. So here's a summary of, yeah.
So you're talking only about Euclidean space?
Yes, I'm only talking about Euclidean space. So the bound, it's like d, it's, I forget exactly the number, but you can kind of copy this for, I think, any LP norm for p greater than or less than or equal to, greater than or equal to. One of those, you can do something fancy to come up with a similar instance. But we'll only be dealing with Euclidean distance in this talk.
So it's for randomized too?
Yes, because the reason is that if you take a randomized algorithm and just take an average of like all the possible things you could play, it's still a feasible point and it costs less. So there's no advantage to playing randomized in this setting. So here's the main progress that we'll be talking about, and this is also going to serve as the outline for the talk. So first, there's a paper that did something called recursive centroid, and that was the first polynomial algorithm for the nested case, and it got d log d. And this was refined to a square root d log d for the nested case, which is basically optimal, give or take a square root log factor that no one's too concerned about.
Point to the things that you're talking about. It's
with the mouse, is that okay?
either way.
Okay.
Sorry, CJ.
It's okay.
Backseat drive out here.
No, it's okay.
I'm lost.
That's okay. This is your talk too. So, right. So this algorithm right here, d log d for the nested case, was improved to a square root d log d, also for the nested case. Then in order to generalize this idea, there was something called the work function, which was brought into play, and the combination of these 2 ideas, plus a lot of other ideas, led to the first algorithm for the general case. And then also at the same time, so this is actually 2 separate papers by the same 4 authors, but in the same papers they gave a separate algorithm, which is just this beautiful, elegant algorithm called the Steiner point algorithm, which is very clean. It has a very clean analysis, and it's O of D competitive. And using the work function together with Steiner point will be the main, ultimately the main goal of this talk, and that gave a D-competitive algorithm for the general case, which is obviously a significant improvement over exponential dependence. So this is about it for introduction. Does anybody have any questions up to this point? Yes, yeah.
Just to be pedantic, I think on the third paper, on the left line, they had a view of OS plateau.
You're right. I cited him later in the talk. You're right. Thank you. Okay. So the first part, we're going to talk about the idea of the centroid for chasing convex bodies. So in this section, I'm just going to talk about the nested case. So forget about the general case. We're always talking about nested for the next few minutes until otherwise specified. And the basic idea is I'm just going to play the centroid of the current feasible set at every single time. And for the moment, we'll assume that the feasible set is bounded so that the centroid is well defined. We'll deal with that assumption in just a second. The motivation behind doing this is Grunbaum's theorem, which says every time I cut off the centroid of a convex set, it decreases the volume of that set by a constant, so that over time I get exponential decrease in the volume of the set, and it might be a nice way to track progress. So now to deal with the kind of boundedness assumption, if I'm working in the unbounded case, I'll employ a sort of guessing and doubling strategy that will allow me to work within phases on bounded sets. So I'll start a phase and calculate opt just using like some offline calculation up to this time. I can figure out what the optimal cost is. And I'll now make a ball of radius 2r centered at the origin. Again, r was the cost of opt. And I'll just play the intersection of my feasible set with this restricted ball. And I'll run this until I get an empty intersection between this bounding ball and the feasible set. At the point when I do this, the optimal algorithm has to have moved outside that ball. So it for sure paid at least 2r. And I can safely assume that the cost of the optimal algorithm has now doubled. While in the meantime, what I'll try to do is bound my cost within the phase to be some function of d times the diameter of that initial set that I was working with. And that diameter is bounded itself by, I guess this should say 4r, not r. But the diameter of the set is bounded essentially by opt, so that within each phase I'm paying the same constant times opt. And since I'm doing this within a doubling framework, the only real phase that matters is going to be the last one, and I'll end up paying like order of f of d times whatever opt is paying at the end of the day. So this is one of the most important slides in the talk to make sure you understand for going forward. So any questions on like how this reduction is working and how the kind of doubling works?
So is this important even if I don't care about the unbounded case? Because I didn't quite catch.
Right. So it is for the reason that if I'm given, say I have some, I start with some. Okay, we'll have to work with the green. So this is my initial convex set, and say the origin is right here. So it's like very, very close to this really large set. So the opt is just this tiny little cost right here, but I don't want to move all the way to the center of this, right? Because then I'm killing myself on the first step. So I'll restrict myself to some little ball around where I started, and then gradually grow that as I need to. That's a good question.
So CJ, is
Yeah.
it fair to say that if somebody told us opt is going to be R, then we just want to be competitive against R?
Yeah, exactly. Right? It's the doubling framework essentially allows us to do this kind of upfront guarantee type analysis that Anupam is suggesting here. That as long as we pay f of d times the radius or the diameter of the first set, then we're in business. All right. So now I mentioned the centroid algorithm as an idea, but it actually doesn't work, and here's an example to show this. So what I'll do is I'll alternately give these kind of slanted trapezoids, which will force the center of gravity to go kind of over to the right here. But then using the bottom of that, I'll give a rectangle, which will push the center of gravity back into the middle. and then I'll give another slanted trapezoid, and I'll always have a little space to make this trapezoid that will force the center of gravity to go some constant fraction of the width of this rectangle over, and just keep repeating this process. And since I'm always moving a constant fraction of the width of the rectangle, I get an unbounded cost on my algorithm, whereas the cost of the optimal algorithm is bounded just by the diameter of the initial set. So this is not a competitive algorithm. However, it leads to some ideas that gave a competitive algorithm. So the first algorithm that we'll talk about is called recursive centroid. And the idea here is that instead of just always playing the centroid, after a certain time I'm going to do a recursion on what we'll call like the skinny subspace of the feasible set. So in the previous slide, at a certain point this rectangle got very, very skinny. And then I just only want to move in the direction of the height of the rectangle and just artificially restrict myself from moving back and forth left to right. And this has two advantages. The first is that since I'm restricting to a smaller feasible set, it makes my steps smaller, so I'm paying less at each step. And the second is that when I run out of space to kind of play within this recursion, meaning I get an empty intersection between my current feasible set and the recursive subspace, then that means I can get a cut which is actually parallel to that recursive subspace. And this will shrink the feasible set in the direction that I want to shrink it in. It won't just keep kind of flattening this rectangle, but it'll shorten it horizontally as well. And I'll show this in the next slide by illustrating this algorithm on the same bad example that I just showed you for centroid. So the first step, it'll kind of do the same thing as the centroid algorithm did because there's not really a skinny direction yet. And maybe the second step too. But now at this point, maybe we'll say that the height is considered a skinny direction. And so we'll start running recursion on just this little part of the feasible set. So kind of imagine that alg is just thinking about that red line there, and when I get a new feasible set, all I care about is the intersection with that subspace. And alg will just move to the centroid of that intersection. And now say at the next time, I'll get a set which doesn't intersect that subspace anymore, so I forget about the recursion's over, I jump back to the centroid in full dimensions. But now what I've gotten is a cut which is parallel to S, which I'm calling the skinny directions of this set. So now I've actually halved the width of the set and basically halved the diameter. And that is a much better notion of progress because when I'm halving the diameter, I can start kind of working in this similar kind of charging against the diameter framework that I had before, and I'll get a geometrically decreasing cost. So this algorithm ends up being d log d competitive, and I won't certainly get into the proof of this, but just the one-line summary of the main idea there is that we tracked the kind of the notion of progress was a projected volume rather than the entire volume. And this, you take the feasible set and project it just onto the directions where it's fatter and ignore the skinny directions so that when that volume decreases, the volume of that projection is, it's blind to exactly how skinny the skinny directions are. So if we just keep making the skinny directions even skinnier, that doesn't register as progress. And this gives like a more honest notion of how much progress we've made since the beginning. Yeah, Anish.
Can you figure out what the skinny directions are?
So it's just set by some certain parameter. I mean, there's like some delta such that if the width in this direction is less than delta, it's skinny, and otherwise it's fat. And that delta is, based on what it needs to be for the analysis. But it's a very binary choice. It's either skinny or not. And so this was improved by Bubeck, Lely, and Selke. And the way the main mechanism of this improvement was that they measured the centroid using the Gaussian measure rather than using the uniform measure. And the effect of this is that since the Gaussian measure is heavily concentrated kind of around the origin, what you get is that most of the mass, regardless of the shape of the feasible set, essentially most of the mass is sitting right near the centroid. So even when you cut off the centroid, it doesn't move very far. And this reduces the motion on each individual step enough to get it down to square root d log d.
So where is the origin?
So the origin is where you start.
So where your current place? I mean, or where you actually start? Sorry.
Where you start.
Oh, that origin.
Yeah, the point that you started at before you got any convex set was the origin. But like even as you get further out, like when the feasible set is further out, it's still the Gaussian measure is dropping exponentially the further away you get from the origin. So you're still concentrating the mass around roughly where you're sitting right now. And then the key fact that they also use is that Grunbaum's theorem still holds for centroids in the Gaussian measure. All right, so just to recap
Just conceptually, what happens on the the centroid example when you use the Gaussian measure? It just moves in that way, just not.
So they're still using the recursion. They're not doing just the Gaussian centroid. They're still using the recursion. Yeah. So to recap this first section on centroid, the naive centroid algorithm failed. It was kind of not sensitive enough to the shape of the convex set. So we fixed this using this recursion strategy and tried to move only in the skinny directions and eliminate the movement in the other directions. And this got optimal up to square root log with the Gaussian improvement. Yeah, Nish?
So if you don't use the recursive strategy, do you know how bad the Gaussian centroid can get?
I don't. We never asked the question, so I don't know. Yeah.
The centroid thing is a bit weird because there's no benefit in actually moving into the interior of the shape. Like you can just stop on the boundary.
Right. So this, it ends up being like you want to maybe stop at the boundary, but it ends up not really improving anything. I mean, you can pretty easily construct an instance that forces you to make the same motions. Yeah, Boris?
I mean, I might have asked this the last year.
Yeah.
So is there any better example even for general case for even 2 dimensions? Or like square root of d literally is the best?
Like 1.5, I think, but nothing asymptotic. Like I think for dimensions, specifically d equals 2, someone got like a 1.5 something. But basically square root d is the lower bound.
Okay, but not literally.
Yeah. Right, any other questions? It's a good time to pause.
And that example is also nested, or the one which goes beyond square root 2?
I don't remember actually. Probably not, is my guess. All right, so now we're going to talk about something called the work function, which will motivate sort of a reduction from the nested case to the general case. The general framework for how this reduction is going, or how we're going to try to do this reduction, is that we're going to imagine that we're given some general instance of, we're not necessarily a nested instance of the problem, and we have some f of d competitive algorithm, and I want to now come up with a sequence of sets omega t, such that it is a valid nested instance. So they're convex sets and they're nested. The algorithm, if I play the algorithm on these omegas, then its cost is only going to be something like f of d times the optimal cost on the original sets. And that my algorithm would not only put out a point which is in omega, but if it puts out a point which is in ki, then it's a feasible point, and what I've actually given is just an algorithm for the general case. And so this would give me a reduction from the general case to the nested case. Where we're going to look for this is this thing called the work function. This has been studied a lot before. It's used in the current best algorithm for the K-server problem, and it's also been used in algorithms for the MTS problem, so it's gotten a lot of traffic in this area before. The definition is that it's for each fixed t, the work function for a point x is how much it costs to satisfy the first t request and then get to my point x. Right, so there's a different work function at each point in time, and it's defined for all points x in the space. So as an example, if I just have one set and my point is inside the set, then the work function at that point is just the distance that I had to travel to get to that point at the beginning. But if I take a point outside the set, then what I have to do now is pick a point inside the set, move there, and then move from that point to my point outside the set. And I add up these distances to get the work function at my point x hat. So, make sense? The set that we're going to care about is a sub-level set of the work function. So here I've given an example where this is the, I'm just going to look at time 1 where I've gotten this is my original convex body. The optimal point at this time is just to project onto that body. And this black line right here is all the points whose work function value is exactly equal to 2r. And by the convexity, everything inside of this circle is going to be the sub-level set of the work function, where I'm just going to, I'll cap it at 2r. And again, r here is always going to be standing in for roughly what opt is. And so this is going to be my candidate set for how I'm going to try to construct the sequence of omegas. And yeah, no
Could you show the thing again? I was still looking in the picture.
Okay. So this set here is the feasible set that or the request that I got at time 1. R here is just showing what opt is. Like this opt should have gone from 0 straight to the set.
Okay.
And then if I'm, say, this point right here, the way I would get there is I'd travel along A, then along B. And the sum of these two distances is 2r. So that this is the work function value at these points is all 2r.
Somehow just to think, so your the feeling is the next bigger object might contain omega 1. So you kind of want to track how expensive it is to move to omega 1. Is that?
So we'll get to what we're going to do with omega 1. I mean, this is going to be the rest of this section, basically, is analyzing kind of how does omega 1 line up on these 3 objectives, or the sequence of omega t's. Right? And just to be clear, the way that omega is changing is it's just changing based on what the work function is changing over time. So the first thing I'll show is convexity of the work function.
This r is really r of t. So
yes, it is. It is a function of t, but it stays. I'm thinking about like one phase within this doubling framework. Well, I'll fix r at the beginning of a phase, and it doesn't change, even though the opt is increasing throughout the course of that phase. R is staying the same.
I don't understand. Sorry. The algorithm you're going to present is going to recompute all the sets omega 1 from omega t when it sees the t plus 4 set or t set.
So
I don't understand your question, Boris.
Index 1 to t for k and the index 1 to t for omega should be.
No, they're the same. I mean, imagine that everything is all one phase. Okay, the first phase opt moved r, or the first step opt had to move r. Okay, and then up to time t, opt has not moved more than 2r.
So what do you mean by opt? Sorry, what do you mean by opt? Because there are some problems. Like it's a problem basically when you see 4 little t sets. So when you may say opt, you mean that it's opt for that subproblem, or you mean eventual opt?
I mean opt up to this point in time for the subproblem.
Okay, so in other words, the set omega 1 up to omega little t are going to be recomputed each time you're going to see a new set.
Yeah. I'm going to have to recompute the work function. The value of r is only changing when I get up to a point where, up to this point, I couldn't have, in the offline, I couldn't have gotten it in less than 2r. But the only thing that I'm recomputing at each time is the work function value of the different points.
So because Brazilian notation say algorithm of omega 1 omega t, but again, it doesn't take omega 1 omega t because really
It does. We'll get to this. I mean, what I'm going to do is play the algorithm. This algorithm is a nested algorithm. And I'm going to show that these are a nested instance. But let me get there. So the first thing I want to show is that these sets, yeah.
So, Boris, think of R as being given by God. R is a fixed quantity.
math is.
Good. So R is something given to you, and you're never going to change R. And you are guaranteed that opt will pay at most R. And you want to be some constant times R. So R is some fixed quantity.
Okay, and then you do the geometric series argument at the end.
We do the geometric series argument and then we finish.
Yep. Thank
So
you,
R
Arnold.
is something fixed
It's
for.
it's an upper bound or not.
It's an upper bound.
Okay. So let me show you that the work function is convex. So if I imagine taking 2 points and some convex combination of them, then the way I'll upper bound the work function of that, the convex combination point, is I'll just take the optimal paths to my points x and y and take the equivalent convex combination of those two paths. So this is going to remain a feasible path because my feasible sets are convex, and by the convexity of the norm, the cost of that is going to respect the convexity of the work function. And so that shows me that my sets omega t are convex because of the sublevel sets of a convex function. So the next thing is the nested. And to show this, I just need to show that the work function value is going to increase over time for any fixed point x, because then any point which has work function value 2r at time t plus 1 certainly had even smaller work function value at the previous time. So that'll show me that omega t contains omega t plus 1. And this is simple because the work function at time t is just how much it costs to serve the first t requests. At time t plus 1, I had to serve more requests. So the cost can only increase if I have to serve an extra request. So far, I've checked off the first bulletin, or the first bullet here. I've got my desired kind of convex nested instance. So for the second one, it's the key fact here is that the set that I'm chasing, the sublevel set, is contained in a ball of radius 2r centered at the origin, because anything that's further than 2r away, I have to pay more than 2r just to get there from the beginning of time. And of course, it's only going to increase over time. And the diameter of that set is then at most 4r, which again, if we're thinking of r is equal to opt, or r is some upper bound on opt, then the diameter is going to be a constant times r. So when we give our algorithm, which is going to be playing, or who's going to have cost some function of d times the diameter of the original set, then it's going to be, again, a function, an order of f of d times opt. So the last thing that we have to think about is the feasibility, is whether our algorithm is going to output a point xi, which is actually in ki. And the problem is that it won't in general. So this is just the same drawing that we had on the previous slide of what k1 and omega1 are. And the issue here is that omega is not contained in t. So if all I know about my algorithm is that it's going to play some point in omega, then I have no guarantee that that point is going to actually be in k. And therefore, this framework does not allow me to give a black box reduction for any algorithm for the nested case to give an algorithm for the general case. And maybe you want to try projecting onto KT at each step and say, oh, maybe that doesn't incur too much extra cost. But it just ends up being prohibitively expensive to do that. There's not, certainly in none of the frameworks that we were looking at was there an obvious way to bound that cost. And I think that this really touches on a challenge, which is a challenge for the work function in this problem, and it's a challenge for the work function in any context that it's used in, which is that the work function itself is defined as an optimization problem for every single point x. And it's really challenging to get a good handle on what exactly the work function is doing. And we showed this convexity and increasing property, and we're only going to use one more property of the work function for the entire rest of the talk. There's really not that much that we can say about it concretely. Okay, so we don't get the feasibility that we wanted, and this reduction framework fails as such. But it can be modified, and it was in this paper. Again, Bubeck, Lee, and Selke, same one. And they use this kind of general idea, and they define the set omega hat, which is a little bit like omega, but it's a little bit more complicated. And they had to use a lot of sophisticated machinery to get the volume dropping arguments to work when they were doing it in the general case. And they ended up getting something that was 2 to the order d competitive. So I'm not going to talk too much about their algorithm, but it is in theory possible, and this work was out there in the ether of you can kind of define this set omega and do this sort of nested instance within a non-nested instance. And just to recap everything, so I've got, I'll kind of my takeaway from this section is that I constructed this instance, and it is a valid instance that has the same cost, and it just has this feasibility issue. And this is just kind of keep that snapshot, is that we have this instance that was constructed using the sublevel sets of the work function, but feasibility is a big question mark. Any questions at this point? Okay. The last part of this talk is, to me, the most exciting part, that will start with this idea called the Steiner point. And this is really just a very, very clean idea to replace the centroid idea. The Steiner point it's a different way of defining the center of a convex body, and it has a long history within convex geometry. It dates back to the 1820s. And it has one nice property that it has is called, it's Lipschitz with respect to a notion of distance between two sets called the Hausdorff distance. Basically what it says is if you have two sets that are kind of close to each other, then their Steiner points are also going to be relatively close to one another. And in the context of our problem, that means if my feasible set doesn't change that much, then the Steiner point also shouldn't end up moving that much. So it sort of motivates the use of it in this algorithm.
Is not centroid continuous?
It is. I think it has a worse Lipschitzness. Is that correct, Anupam? You don't remember?
It'll be very poor Lipschitzness by exactly the same kind of
Oh.
movements.
Oh, yeah, right.
Take a rectangle and you shave off this kind of thing. Exactly the kind of examples that CJ was showing. The Hausdorff distance changes along the vertical side, but you are moving horizontally.
Yep. Thanks.
So it's not even bounded Lipschitz.
Yeah, okay.
Yep. So what is the Steiner point? What I do is I take a random direction, and then I find the extreme point of the convex set in that direction. And just keep doing this, and I average over all possible directions of whatever that extreme point was. So that gives me some point inside the body. And another way to think about it, I'll get you at the end of the slide. Another way you can think about this is if you have a polyhedron, then you can take the normal cone at each of the extreme points and use the size of the normal cone as the weight for a convex combination of the extreme points, and that gives you the Steiner point. Okay. Question?
So what do you mean by extreme point? Do you mean like every boundary point, or?
Not necessarily a boundary point. Extreme point meaning that it can't be written as a convex combination of two other points in the set. So for a formal definition, this is essentially the definition that I gave on the previous slide. Yeah, Kirk?
Just intuition, like if you had a tall, skinny rectangle or triangle. Or something.
I'll get to that in another slide.
All right.
This is the formal definition. It's the average over all directions of the extreme point in that direction. And this function sk, so there I'm using the gradient, the function sk by itself is a little bit more important for this talk, which is defined as the maximal possible inner product I can have with this direction over the set. And this second definition I've given here is equivalent by some form of Stokes' theorem. The equivalence is not terribly important. Just the thing I want to highlight is that this is the definition that I gave on the previous slide to illustrate the intuition, but this is the definition that is algebraically more convenient, and this is what we're going to be working with for most of the rest of the talk. And I'll repeat this definition as needed throughout the talk.
Do we need to understand it right now?
What?
Should we understand the second definition?
Oh, okay. So this definition, you take, it's a little bit funny of a definition because what you do is you take the direction and then you scale that direction by how far you can go in that direction in the feasible set, or in your set K. And then you average those together. Now the thing that's mysterious about the second definition is that it's not clear that from the second definition that the Steiner point's actually in the body. Whereas in the first definition, it's a convex combination of extreme points of the body. But here, this thing, sk of theta times theta, is not actually a point in the body. It's just some point. And then when you average them all out and you multiply by d, then it magically ends up in the body. And again, the equivalence of these two definitions is like some cute little proof with Stokes' theorem that I'm not going to get into, and I will leave as an exercise to the viewer.
You're assuming the body contains origin.
Convex.
It doesn't need to contain the origin?
No, does not need to contain the origin. Which is why this is so surprising, right? That gives you a point in the set. But these, you can just show using Stokes' theorem that this integral equals this integral, and this one is clearly in the set. So this allows us to now state the Steiner point algorithm for the nested case, which is move to the Steiner point. That's the whole algorithm. You just move to the Steiner point every single time. And this algorithm works like magic. And so I'll illustrate this again on the same bad example that we had for centroid earlier. So now when I take the normal cones of all the extreme points of this trapezoid, so the weight is more evenly distributed between the left side and the right side. So I don't end up going so far over to the right. And now I get a rectangle and I'll jump back to the middle because the weight is evenly distributed among the corners. And as I get a thinner and thinner trapezoid, the size of the weights of the normal cone get like closer and closer to being right angles for all of them. So I end up staying closer and closer to the center as the set gets skinnier. And if you kind of look at what's happened throughout this algorithm, we've almost done the recursive centroid algorithm in a smoother way. So without actually defining the skinny subspace, the Steiner point has just restricted our motion to stay very close to where that skinny subspace would have been. But this is without this kind of arbitrary binary choice of what's a skinny subspace and what's not. So it's a very nice algorithm, and it's order D competitive, which is comparable to the recursive centroid algorithm. It's also memoryless. In the recursive centroid algorithm, you had to know where your where the subspaces that you're recursing on were. This is memoryless. You don't need to know any points you've played in the past or any sets that you got in the past, and it's just beautiful. This algorithm has a one-line statement and a one-page proof, which I'll show you on the next line. So if you don't understand this proof exactly, don't sweat it too much. It's not the most important part of this talk. But the cost of the algorithm is just the sum over all time of the distance of consecutive Steiner points. If I sub in the second definition of a Steiner point, then I can replace that with the integral. I'll combine the two integrals so that I can factor out the theta and just take the difference of the two support functions. Now by using Jensen's inequality, I'll move the norm inside the integral. And then after I've done that, I'll switch the order of integration and summation. No problem there. I'm integrating over directions, which have norm 1, so I can get rid of that term from the integral. And now since it's nested, and the support function is a maximum over points in the body, that means that it can only get smaller over time because I'm just getting a smaller and smaller body. So I'll get rid of the absolute value. Now the sum telescopes. And now since I have a bounded body, the total amount that the support function can change is just the diameter of the body. So this integrand is always bounded by the diameter times d, and the diameter was like opt. So that's the whole proof. And so if you didn't quite catch that, again, it's okay. But like the takeaway is there was nothing clever in this proof. It's just like very obvious steps, and there's like 3 of them, and then you're done. And that's the whole algorithm and the whole proof. So really just a sweet algorithm. We'll take this a step further now and show how to combine it with the work function to get an algorithm for the general case. And I'll remind you of the framework that we had in the last section, where when we defined omega t as these sublevel sets, it gave us an instance of the nested chasing where the algorithm is paying, our order d times the optimal algorithm. Okay, it said order f of d, but it's going to say order d now, because instead of playing an arbitrary algorithm, I'll play the Steiner point. And the amazing realization is that it's actually feasible if I play the Steiner point. And as soon as I prove that it's feasible, that immediately gives an order d competitive algorithm for the general case. Because all the framework of the cost and the validity of the nestedness is there from before. So all I have to do now is show that the Steiner point of omega t is in the current convex set. So this little box down in the corner will just be a little bit of a guide if you need it. So the goal of this is, again, to show that the Steiner point is feasible for the current convex set. And here's just the reminder of the definitions of what omega t, the Steiner point, and the support function are, in case you need to reference them throughout this. So step number 1 is that I'm going to assume that my convex set is actually a half space. And the reason I can do this is that if I show that the Steiner point is on the correct side of every half space that contains the convex body, then it has to be inside the convex body itself, because the intersection of all those half spaces is the convex body. And since everything's translation invariant, I'm just going to assume that this goes through the origin, and that won't create any problems. And an important kind of correspondence that I'm going to look at is the reflection of a point over the boundary half space, or that boundary hyperplane of this half space. So I'll define this thing y hat as that will just be the point y itself if it's already feasible, and it'll be the reflection of y into the feasible set if the point y is not feasible.
Repeat why the first one was without loss of Tillman.
Because what this proof essentially shows is that for any half space containing the feasible set, I'll show that the Steiner point is in that half space. And so it's in the intersection of all the half spaces, which is the feasible set. All right, so the first important claim I want to make is that any point y which is in omega t, its reflection is also in omega t. So the picture here is I have some set omega t. It's maybe partially in, partially out of kt. If I take my point y to be originally in omega t, then there's really nothing to prove because y hat is equal to y as I defined it on the previous slide, so that's kind of boring. But the more interesting case is if I take my point y, which is inside of omega t but outside of kt. And I'm looking at its reflection, and I want to show that its reflection is in fact inside of omega t. So since omega t is defined by the work function value, I need to get an upper bound on the work function of y hat. So I can get some point z such that the optimum path to get to my point y is I'm going to do whatever I do and come to z. That's where I'm going to satisfy the request kt, and then from there I'll jump to y. And however much I paid to take this path is the work function of y. But if I just taken that exact same path and instead of jumping to y, I jump to y hat, I would get a path that's the same cost because the distance from z to y equals the distance from z to y hat. And that gives me an upper bound on the work function of y hat of the work function on y. And since, again, it's a sublevel set, so that means that y hat is inside. And we're good to go. Okay? So the way I'll kind of remind you of this is if you highlight the section of omega t that's outside of kt and now just reflect it over. So that reflection will also be a subset of omega t. And I'll pause here to note that at this point you should be pretty convinced that the center is going to be on the right side of this half space, because if I just looked at this subset of omega, by its symmetry, the center of this set, for some reasonable definition, the center should be on the half space. And then by adding more mass to omega t on the side of kt, I'm just biasing the center over towards kt. But I'll go ahead and prove it. So the Steiner point, if I can think of it as like, I sample a random direction, find this point that maximizes the inner product, get whatever that expression is in the integrand, and do this a bunch of times, and I average them out. If instead of doing this process by sampling one direction at a time, I actually sample two directions at a time, which are specifically reflections of one another. So every time I sample a direction, I'm also going to take its reflection. And I'll just combine those two into one term in the integrand. And now I'm integrating, instead of integrating over all directions, I'm only integrating over the directions that are negatively correlated with the direction A. So I'll start with some direction, and I just want to show that if I take that integrand right there and take its inner product with A, I'll get something positive. So then when I take the inner product of the entire integral with A, I'll also get something positive and therefore inside of kt. This is what I want to show. I'll just split up that inner product by taking out the sum and taking out the support functions because they're constants. And since theta and theta hat are symmetric with respect to this half space, which is defined by A, the inner product of theta and A is the negative of the inner product of theta hat and A. I'll make that replacement. And now theta hat's the one that's positively correlated with A, so I'll just divide by that term and not change the sign of the inequality and rearrange to get that I'm trying to show that the support function of theta is less than the support function of theta hat. So this is all I need to show now. And if I look at the support function of theta, I get some point z theta, which realizes the maximum of that inner product. I can reflect that across KT because of the reflection lemma that I had a couple slides ago. And the inner product is going to stay the same. But now there's some other point which actually maximizes for theta hat, that inner product, and that's the support function of theta hat. So the support function of theta is less than or equal to the support function of theta hat, which means that this whole expression right here has positive inner product with A, which means this integral has positive inner product with A, which means the Steiner point is feasible, which means that the algorithm is OFD competitive. So that's the whole proof. So just to recap the main theorem, the algorithm was I just play the Steiner point of this sublevel set omega t. And the proof, going back to the work function section, we showed that the sets omega t are convex and nested. I had this feasibility lemma. And to me, the kind of the key picture here is, again, thinking of the part of omega t which is reflexive over kt, and then there's the extra mass on the side of kt. And then the algorithm will pay order of d. Order of d is coming from the analysis in the nested case of the Steiner point algorithm, and that's order d times op. So we have an order d competitive algorithm. Any questions? Right, before I conclude, I want to...
Proves that omega t cannot be, like, say, disjoint from kt or something. That follows from that, or is that...
It does follow from that, right?
Is that something, like, even more obvious?
Yes, because the cheapest opt itself is sitting in kt. Right? Whatever point minimizes the work function is sitting in kt, and we know that that has to be less than 2r. One other thing I'll mention, since I think I'll have enough time, is that there's a cherry on top of this theorem, which is the other half of our paper, which is that you can actually implement this efficiently. But there's not really anything interesting going on there. You just randomly sample a bunch of points and compute the Steiner point in that way. And most of the technical work there is just figuring out how you compute the work function in some efficient manner. But yeah, not...
How are the convex sets given to you when you implement?
So there we assumed without loss of generality, or okay, we assumed it's not necessarily without loss of generality that there are in fact half spaces. We think that if you're given a separation oracle, it should be enough. We didn't quite hammer out the details.
Would you be okay with the sampling access, given that that's what you needed? Oh, I guess work function is the more complicated.
Yeah, you have to be able to compute the work function. You have to optimize over the sequence of sets. So I want to give a fair nod to Mark Selke's paper, which was published at the same time as ours. And it did a similar algorithm, but I think an even more elegant actual statement of the algorithm. So what he did is it said, instead of playing the Steiner point of some made-up convex set, he defined the Steiner point of a function. And he did this using, his definition is, it's the average over a theta in the dual ball of the gradient of f, of the Fenchel dual of f evaluated at theta. If this doesn't make a lot of sense to you, I'm going to just refer you to the paper. I don't know that I can really explain much intuition on this in a couple minutes. But I'll leave it as an exercise to show that if you take the function f is just 0 on some convex set and infinity everywhere else, then the Steiner point of that function is the Steiner point of the convex set. So this is like a very natural generalization of the Steiner point from a set to a function. And his algorithm, without even doing kind of a guess and double sort of framework, just plays the Steiner point of the work function every time. So one sentence statement of the algorithm. The analysis is requires a little bit more machinery, but it follows similar ideas to that of the nested Steiner point case and doesn't really have anything earth-shattering in it. And it also has the advantage that it works for an arbitrary norm, which is pretty cool. Our algorithm works for the Euclidean norm. Where it breaks down in other norms is that when you reflect a point over the half space, it changes the norm of that point. So this kind of symmetry lemma that we had breaks down. So just a couple open questions. The biggest one for this particular question is whether the general case can be gotten down to square root d, since we know that it's between square root d and d. My guess is that probably square root d is the truth, but I have no idea what kind of algorithm would get there. I don't think that I don't believe that the centroid algorithms are going to get down to square root d for the nested or for the general case. And also, it would be nice if we could apply this to other related problems that I mentioned at the beginning, paging, MTS, case server, which we've seen use of the work function, but not the Steiner point. And it'd be nice to see if the Steiner point could be used for any of those. That's all. Thank you very much. Happy to take questions. Kirk?
Yeah, so like you said earlier, you wouldn't have expected a priori the work function is so useful because it's hard to analyze. Is somehow
Yeah.
reasonable takeaway message is like somehow you didn't really have to understand it very well?
Yes.
The properties used were very
100%. I mean, like, if you asked me, if you gave me 3 convex sets and said, after you've seen these 3 sets, where would the algorithm play? I have no idea. Like, I don't understand this algorithm on like any sort of like intuitive, deeper level exactly because of the work function. I understand the Steiner point. I don't get the work function. Rajesh?
So I mean, I guess if you don't have, I guess it's hard to understand how the algorithm works. You don't have an example where your Steiner point fails to give you better. But do you have a lower bound saying that the Steiner point of this particular application gives you
Good question. So in the nested case, they do have such a lower bound.
Okay.
However, it's difficult.
In this case, you're just playing Steiner point.
Yeah, when you're just playing the Steiner point in the nested case, they actually have a lower bound that gives that D is the right answer. The challenge in doing it in our algorithm is that I'm not chasing arbitrary nested sets. I'm chasing nested sets that resulted from the work function, and I might not be able to fiddle with them so precisely. So I'm not actually sure. Kevin, Kat?
Yeah, for these special cases like paging, case server, I guess for those things randomization is kind of key, right? But somehow this unification, because of convexity, the
Right. So where randomization would come into play there is that we'd be giving, like, convex body chasing can only be used to get a fractional algorithm for paging or for case server, and then you'd need to use randomization in order to turn that into an integer.
But I guess you can view those randomized algorithms in this 2-step thing where you have deterministic phase and then some randomized round.
Perhaps, yeah. Yeah.
So you mentioned that you're given some reasonable like encoding of convex sets, you have an algorithm.
Yeah.
Did Mark's paper as well for general metrics?
Good question. Not sure. Like he doesn't say anything in the paper, but I don't. It's not clear to me a priori. Like I don't have a sense of how to calculate the Steiner point of the work function. Like, is that an easy thing to do or not? I don't know. Else?
I guess I have a related but possibly nonsensical question.
Yeah.
So as far as computing the Steiner point is concerned, you can like just sample random directions and then like approximate your interval.
Yeah.
Do you have any hope of doing like computing a Steiner point deterministically?
It's a good question. It's something that I think Guru has been thinking about. Like, is there a better way to compute the Steiner point? I don't know. I'm not aware of any algorithm that does it. Is there any hardness result on that we know of?
Only certain oracle models you could say that, look, if I gave the body to you only via separation, things like this.
Sure. Boris?
So you mentioned that the Steiner point is a Lipschitz function on a space of convex bodies.
Yeah.
And it intuitively made sense why it defeats that example. But then if you prove that the Steiner function gives you ordered decomparative algorithm, you did not use this, the Lipschitz property directly.
Correct.
You used the definition. So as far as I understand, you cannot use the property as a black Lipschitz property as a black box in a proof. If yes, the second question would be: is the Lipschitz constant is optimal among space of all functions, which are sections of this bundle?
Okay, I didn't understand the second question.
Is it better than centroid, the better Lipschitz constant?
Sorry, one more time?
Is there a better way to select a point from a convex body so the selection function has better Lipschitz constant than the Steiner point?
I don't remember the answer to the question. No? That's optimal?
The Steiner point is the optimal selector.
Okay.
In fact, They're equivalent. Yeah, there's a nice survey of Benjamini Linden's cross, which shows, which gives the proof of this, but it's been known for some time. So, and yeah.
Any more questions?
Okay, let's thank CJ again.